this one course about incoherent waves, or let's say, or incoherent treatment and processing of electromagnetic waves. Now, from now on, we will switch to coherent processing of electromagnetic waves, which more or less means that the phase, I'm just trying to, okay, which more or less means that the phase will get into the picture. So we will start learning a kind of processing which will be able to some extent to mimic what is done by physics. So my goal, if I'll be good enough to teach you at the end of this course, will be that you will be able to write a code, like in MATLAB or whatever a language you like, but we will just use MATLAB. So you will be able to write your codes to do radar processing. And you will be able to well, understand radar imaging, and also to design a system for radar imaging, and also to you will also know how to use a system of this kind for different applications. So like I don't know, just imaging or detection of change detection, interferometry, polarimetry, tomography. So the basic idea is that at the end of this course you will be able to, let's say, to look at this world of the world of remote sensing and Earth observation, not just like students, but as people who are trying to, who are starting to understand it and maybe would be willing to work in this world. So now, before we start, I think there is something I need to ask you. In the first place, is it dark enough to see, or do you want me to lower the curtain? A bit.
Lower the curtain.
Just a bit. Okay. Good. Just tell me stop.
Yeah, okay. Stop.
Thank you. Is that okay? Okay. So now, what you say? You got the first homework from Professor Monti Guarnieri. You will get 2 more from me, and so this homework will. So if you do these 3 homework, then you will discuss them with me and with Professor Monti, and this will be your exam. If you have no time to do these homeworks, you can give a final exams at the end of the course. For me, you can give it more or less whenever you like. Meaning that if you say that you have no time in January to prepare this exam, you can give it in March, April, whenever you like. Of course, I will only register your exam at the first possibility. So you know that I can only do that like in January and then in July and blah blah blah. But you can discuss it whenever you like. And what else? Well, I've been asked by a student how many people can do a homework together, and my answer is 2. So it's fine for me to receive a homework by a group of 2 people, not 3 and not 4. Okay, so 2 is the limit. So what else? Well, I think that concerning bureaucracy, this is more or less it, unless you have any question. Okay. Okay. So how do I intend to proceed for these classes? Well, sometimes, like today, I will project slides. So these slides will more or less give you the basic information, but they will complemented by exercises at the blackboard. So like, how to say, old-fashioned teaching style. Some other times I would just use the blackboard, and so I'm going to write a lot of equations and so. And some other times I will present you MATLAB codes. So this will be a very important part of this course. I will come here with my PC and I will project you some MATLAB codes. You will have all this material in a dedicated, like, Dropbox folder or something else. I use a Dropbox usually. Are you fine with Dropbox? Usually it's fast, it's convenient, okay. So you do not have to rush to write everything I tell you, because you will get it, especially for MATLAB codes. But I do suggest you to take some notes, because it's better. Everyone has his own way to understand things, and I think that skipping classes and just trusting that you will understand everything is a bit risky. So my suggestion is don't do that. So what else? Well, I will tell you when I will present MATLAB codes. So in that case, you are welcome to bring your own PC here if you want to try it, but it is not necessary. So you can also come without a PC, and you will be able to try these codes at home. So what else? I think it's pretty much it. So before I get started, any question or something I might have?
There is deadline to discuss the homework, or
the one by Monty, he said it's 1 month. So
yes, for yours.
more or less the same. So I would say maybe we will have to coordinate for the last one, because it will be across Christmas holidays. So okay, we'll be fine. And so I think we can get started. So just as a forward, I have so although I was a student of Professor Monti, I have a slightly different style. So I use mathematics a lot more. So my classes will be full of equations, and I give a lot of importance to this, because I want you to be able to read an equation and say, oh, this is a field, this is the derivative of a field, this is my signal, this is the field from my antenna. So I would really like you to be able to read an equation like it is a wonderful book. Okay? I know this is not always easy, but trust me, I think that if you have problem with mathematics, it's just because you had bad teachers. So I want to try this game with you. I will present a lot of equations. You have to swear me that if you find this difficult, you will always raise your hands and say, Prof, I don't understand anything. Okay? And I commit to explain until everything is really clear. Why I do that? Because you will. So this is a course. This is the master course. So you are also supposed to be able to produce something original after seeing this, after attending my classes. And I don't want this to be just download the software tool, written by someone else and applied. I think it is very important that you are able to write something on your own, or if you don't like software, to be able to design your own system. So I consider this very important, so I would like to take this challenge with you. I will try to be as clear as I can. You have to commit to raise your hands every time. Okay? Now, another forward, this first lecture here will be really very difficult. And why? Because I'm trying to summarize everything about waves. You saw a lot of this material in previous courses, like in electromagnetic courses, and also presented by Professor Monti. But I thought that it is a good idea if we, set up on a common language. So I will present my notation, and you will tell me everything is clear or not. Okay. I will also present some differential vector calculus today. If you do not know it very well, do not freak out. So it is not necessary for this course, and what you have to keep at the end is a very short part which just concern the final conclusions and, let's say, the most important threads of electromagnetics. So I think I talked too much, and so I can start right away. Like this. So, introduction to radar imaging. So, radar. Radar stands for radio detection and ranging, and it is a technology to detect a target which stands far away and knowing it and measuring its distance. This is called ranging, to measure a distance, simply by transmitting an electromagnetic pulse at radio frequency and observing the backscatter echoes. And there are some relevant features of radars. First thing, it is an active instrument, so a radar does transmit power, which is good because it means that you do not need an external illumination source. It is better, of course, because you have to pay for transmitting this power. It is based on delays, so at the end of the day, everything a radar does is to measure a time interval. But we will see in this course that it does it very, very, very accurately. So this is the strength of the radar. It can only measure a time delay, but the accuracy is awesome. And then, of course, we are working at microwaves, so microwaves do penetrate through raining clouds. So if you think in the context of space for remote sensing, this is a very nice advantage, because you can have visibility in all weather conditions. And then also microwaves can penetrate into natural media, and so like forest, snow, ice, sand, blah blah blah, which means that you are sensitive not just to the outer boundary of your media, but also to the interior. Right? So you are not just like in optics, where you cannot see through. With the radar, you can see through. So, what is a synthetic aperture radar? This will be actually discussed in a few weeks, I would say, but I just wanted to introduce this technology at the very beginning because it is one of the leading technology for remote sensing now, and it has been such for, I would say, at least 20 years now. So, a synthetic aperture radar instrument employs a radar flown on board the moving platform. So basically, you take a satellite or an airplane or an aircraft or a car or whatever you like, and you mount a radar on this. And as this platform moves along a certain trajectory, you simply transmit and receive, transmit and receive. That's it. Then you do a lot of signal processing, which we will see throughout this course. And what you end up with is a wonderful map. It's a 2D map, of course, not like an optical map. This is a map of backscattering at this particular frequency. So at the particular frequency at which the radar works. And this is a very nice example from Sentinel-1, where you see all northern Italy, or most northern Italy, is mapped by the radar. They say in our field that we are living in the golden age of synthetic aperture radars. And as a matter of fact, if you look at the history of this technology, I would say is quite impressive. We had the first systems were launched in the late 70s. The first one was CSAT in space. Well, the principle has been known, we say, since the 50s, but the first spaceborne instrument was launched in the late 70s. And then we had an impressive progression of spaceborne systems. Just to cite a few, the European ERS 1 and 2, the Canadian RadarSat, the Japanese JS. SRTM was a very famous mission by NASA, and they flew the shuttle with 2 antennas to map the global topography. So this mission provided the global mapping of the world topography. Then we had EnviSat by the European Space Agency, which produced an impressive amount of data, and it really boosted interferometric applications. This is an image of an earthquake, as marked by SAR interferometry, so we will discuss this a lot. Again, the Japanese ALOS, the Italian Cosmos Skymed 1, 2, 3, 4, German TerraSAR-X and TandemX. Now we have Sentinel-1B, it is the latest SAR satellite by ESA. Golfan 3 is a Chinese SAR launched in late 2016. So this is an image of Wuhan. This is an island, and so this is the 2 branches of the river of the Yangtze River in Wuhan. The Argentinian Space Agency launched this Sunday the Saturn 1A system, and there are many more systems that are planned, and a lot of research activities to propose the next spaceborne satellite. And so, what kind of applications do we have? Well, of course, imaging. Of course, imaging, and not only. We mentioned topographic mapping, so using SAR interferometry to get a 3D reconstruction of the topography. We have land mapping. Now there is no contrast here, but on my screen you see different colors which are associated by different land use. So based on remote sensing, it's possible to map how the land is used. So like cultivated field, water, urban settlement, and so on. Change detection is very important. This is an example of the changes undergone at Amatrice in Italy before and after the earthquake. And then also deformation monitoring is very important. This is a map where the color scale represents the subsidence rate, so like in millimeter per year, of any point in this map. So for example, here it is reddish, it means that this area is moving very fast, whereas greenish means it is not moving so much. Now if you want to have an idea of the accuracy of this technique, well, typically this is a scale maybe of centimeter, and this is in years. So these kind of techniques are able to map motions on the order of millimeters per year. So it's super accurate. And we mentioned another important feature of microwaves, that is they can penetrate into natural media. And so this means that since you are sensitive not just to the boundary of an object, but also to the interior part, then with the proper system, which in this case is constituted by several orbits, then you are able to reconstruct the three-dimensional, let's say the three-dimensional structure of this object. So you do not only produce maps, so pixels, but you can also produce voxels, so data cubes, where each voxel represent radar scattering from that one position. And this is an example. So this is a tropical forest at P band, so very long wavelength, this big. This is a tropical forest in French Guyana. This is the signal from the ground level. This is the signal from 10 meters above the ground level, 20 meters above the ground level, and so on. Of course, it is not easy to represent an object that is 3D on the board, so we just draw sections. And this is the same on the glacier. You see, this is radar scattering at the surface, and this is 25 meters below and 50 meters below. So this is what your radar can give you. Now, I've just told you a very nice story. So these properties, a few nice photos, and then I told you, wow, this is something that you can use for a huge lot of applications. And of course, is this true? You should question me. So I'm just acting as a magician so far. And well, the answer is yes. Yes. So I am not cheating, but with some effort concerning geometry, electromagnetic waves, and of course a lot of signal processing. So I always like to start my classes with the geometrical principle of localization. So we say that the radar system is a technology to study far off target by transmitting receiving impulses. And so if you allow me to give you just for today a very simplified description, then we can imagine that this is our radar antenna. So we excite this antenna with a signal. So let's say this is the signal that we are transmitting. And this signal does propagate everywhere in space in the form of a spherical wave. If you want, of course, this is not exactly true, because real antennas, as you know from Professor Monti's classes, have a pattern, so they never emit everywhere in space. But for the moment, just assume that we can do that. So you excite this antenna with a certain signal, so a certain function of time, and here you get the signal that you receive at a certain point, let's say P1, is just the transmitted signal delayed by this term, which is the ratio between the distance between your real antennas and your point and the speed of light. Okay, so what you get here is just the delayed signal. Very important, this delayed signal depends on distance only. Okay. If you like, you can assimilate this to the case of a circular wave on the water surface. So just imagine that you are throwing a stone in a lake, and you get a spherical wave, or well, a surface wave, so a circular wave. Let's say spherical wave by and large, and you get exactly the same situation. So at this point, the signal will interact with the target that you have here, and again, as very rough and first approximation, we can assume that this target, so this current P1, will act as a new source of emission. So it will capture the received signal, which is the original signal delay, and it will emit a new signal everywhere in space, which will arrive, for example, at this point P2 after a further delay. So if you want to calculate, what is the signal that I get at this point P2, considering this first emission and this reflection, then it is the original signal delayed by this distance, and then by a further delay by this other distance. So the signal that you get at P2 is the original signal times the total distance divided by the speed of light. This A is just a constant that accounts for, let's say, the strength of the reflection by this object. So, in the case of a radar experiment now, it is the radar itself that receives this backscatter echo. So the signal that you get is S of t minus twice the distance divided by the speed of light. And so, since you know the time when you transmit it, so for example, this is the transmitted signal, this is your received signal. All you have to do is to measure this delay, and so in this case I just put 20 microseconds. You know the propagation velocity, and so you know that this car here is somewhere in space on the surface of a sphere which is centered on the radar and with a radius of 3 kilometers. Okay, this is a basic radar experiment.
Prof,
See,
but in this case, what is the means of measure of S that we are considering?
well, if you, that's a nice question. It depends. So if you refer to a signal as it is transmitted in air, then it can be an electromagnetic field, so like volt per meter.
Yes.
If it is the signal after being received, so the signal in the circuit that is attached at the front end of the antenna, then it is volt or ER or current. In this course, we will assume that this is digitized after being received.
So we are in
it is
signal
just
processing. We are signal processing. So we have a dimensional.
Yes, yes. However, the trick is to put all the unit here in this constant A.
Okay.
So at the end, it is in this constant that you can account for the physical size of the target and so on.
Thank you.
So, what did we say? That this radar experiment is transmission and reception and measurement of the delay between these two signals. So easy. And this means that you can localize your target on the surface of the sphere. So at the end of your radar experiment, what you get is that your target dwells here. Now, let's complicate this further. Let's assume that you have two radars. And so you build two radar experiments. So the first target, the first radar received the signal after 20 microseconds. The second radar, the green one, received the signals after 30 microseconds. So what you know is that the target is bound to lie on the surface of this sphere C1 and at the same time on the surface of this other sphere C2. So the target, if you assume that the target belongs to the plane of this board, then it has to be either here or here. So just two possibilities. We assume that the radar mostly emits in this direction, so real antennas are undirected, and so we can fairly assume that the target is just in this half space, and so we nail down its position in this plane. And this is more or less how a okay, here, with the pins. And this is more or less how a synthetic aperture radar system works. So, since you fly your radar on the trajectories, and for each point of this trajectory you transmit and receive, then it means that you are measuring the distances of the target from every point on these trajectories. So, for every point on these trajectories, you know that the car has to dwell on a sphere with its center on this particular point and with a certain radius. Now, if you intersect all the spheres that you get from on this trajectory, then you end up, and maybe I have a figure. No, I don't. Then you end up with a circle, with a single circle. So the intersection of all the spheres centers on this trajectory, and with the radius given by these distances, shrinks down to a single circle. And so it means that what a synthetic aperture radar can give you is the possibility to localize the target on this circumference. So you know the x coordinate of this target, you know its range, but you cannot tell yet whether the target is here or here or here or here. So you are still missing the information about elevation. How do you get this information? Well, I think it's easy now. So with one position, you get a localizations in 1D. With two positions, it's a localization in 2D. If you have a lot of positions but on the same line, then you still get localization in 2D. So if you have a different position, not aligned, so they have to form a plane, not a line, then your target has to dwell on the intersection of these three spheres, and always considering a single half space, then it defaults to a single point. So this is how radars, or let's say system radars in different position can give you the position of targets in the three-dimensional space. And this brings me to mentioning a technique known as SAR tomography. So basically, it is obtained by flying different trajectories. So for each trajectory, you have a SAR experiment. So from each of these experiments, you can know the position of the target on a certain circle. If you intersect all the different circles, then you end up with a single position. And this is how you get it. So this is it for geometry. I like to start from geometry because I think that it really unveils the very principle of radar localization. And trust me, when you know too much about waves and signal processing, you might be tempted to draw conclusions that are simply wrong, like real life experience of a guy who was trying to convince me that he could get three-dimensional localization using just one or two antennas, because it was, let's say, playing with signal processing. But when you have a doubt, just go back to geometry. This is the very physics of the radar, and you cannot escape it. Of course, the problem here is that I haven't told you anything about resolution. So what is the resolution of my measurement? I haven't told you what happens if there are many targets. So I think that at this point, any of you could write a code where you measure distances from different points, and then by triangulation or by solving a complicated equation, whatever you like, understand the position of a single target. But what I didn't tell you is how to treat the case of multiple targets or a continuity of targets, like an image. And of course, how to form an image. And so, to answer this question, then I need to talk to you about waves. that you know a lot about waves, because you had electromagnetic courses, and then you had the lecture by Professor Monti. But what many people, also many engineers and physicists that work in the field, do not really know is what is radiation. So why the hell does this thing happen? Huh? And so I try to summarize this in a way that you might have missed throughout your courses at Poly. So, radiation. Radiation is transport of energy by electromagnetic waves. So basically, we excite an antenna with a signal, and then an electromagnetic field is emitted, and it travels until it is received by another antennas. So, in this sense, we can say that the electromagnetic field is the taxi driver of our signal. So the signal is information, and the field is what brings this information in space. It is what it makes it travel. Physically, it is always the combination of an electric field plus a magnetic field. We're talking about vector fields, so very complicated objects. It is 1, 2, 3 components, and each component is a function of 1, 2, 3 spatial coordinates by one time coordinate. You cannot have an electric field without a magnetic field, and vice versa. And they propagate with velocity c, which is 3 to the power 8 meters per second. You have a lot of similarities with mechanical waves. So it is a transport of energy, not matter, just energy. And they are triggered by a perturbation. You throw a stone in the water, and you trigger a wave. You accelerate a change, and you trigger an electromagnetic wave. But very important, EM waves do not need a medium to support propagation. So they propagate in vacuum, which is different than mechanical waves. Some classical EM theory. So these are the basics of the EM theory in physics books, and it mostly developed from experimental observations. So you start from the force between two charges, which is called the Coulomb's law. Then the force between two circuits that carry a current. This is the Biot-Savart law. So this is the electrostatic field. This is the magnetostatic field. Then the Faraday normal law. If you have the magnetic field that is changing over time, then you have the automatic generation of an electric field. So if you take a wire and a magnet, and you change the flux of the field, then you have a current. And then vice versa, a magnetic field is generated as the result of the temporal variation of an electric field. And this is the fourth Maxwell equation. You know this very well. So Maxwell's equations provide a very accurate model for the characterization of electromagnetic phenomena over a quite large interval of frequencies. But if you want to study like X-ray and gamma ray and beyond, then you have to go to quantum physics, which I really do not know. So let's say that my experience stops, well, let's say here, more or less. But I am more comfortable here. So microwaves and lower. And very interesting is that Maxwell's equations do predict that EM waves propagate with this velocity, but what is surprising is that they do not tell us anything about the coordinate frame in which this propagation happens. And this is a remarkable difference with respect to mechanical waves. Because you know now, so now my voice is traveling to your ears at 340 meters per second, but if we are in a train, then my voice is traveling at this speed with respect to the train, of course. Not so for electromagnetic waves. So there is this question about in which reference frame this is valid. And for this reason, physicists initially supposed that these waves would propagate in a hypothetical medium called ether, but this hypothesis was put forth by experimental observations, and you can see the famous Michelson and Morley experiment if you want to go deeper in that. Now, a hypothesis that makes Maxwell's equation consistent with experimental observation is that EM waves do propagate in free space with velocity c, which does not depend on the motion of the source and does not depend on the motion of who is observing this phenomenon. And this is really weird, because it means that I launch an electromagnetic waves here, and for the green guy, this wave is traveling at velocity c. For the red guy, who is going in the other direction, this wave is again traveling with velocity c. So this is completely different from the case of mechanical waves, where the velocities should sum up according to the Galilean transformation. So there was a famous guy called Albert Einstein, who, with his special relativity proposed in 1905, successfully conjugated the invariance of EM waves propagation velocity with the laws of mechanics. And this followed from two simple assumptions. First one is that the laws, and S is missing here. The laws of physics are invariant, so they are the same in any inertial frame. So as long as there is no acceleration, then I can use the same physics. The other assumption is that EM waves do propagate in vacuum with the same velocity c, independently on the source and on the observer. Now, based on this very simple assumption, you have all the spectacular results that I think that more or less everyone knows, the time, dilation, distance, contraction, and so. And why am I talking about this here now? Because it provides a very intuitive and simple way to look at EM radiation. So understand what is radiation, why does it happen, and clarify the connection between electric and magnetic fields. So, first thing first, time dilation. This I wanted so this is something I wanted to tell you because for me it really was mind blowing. It is so simple. So just imagine that I want to measure how tall I am. So I just draw a light ray here that goes to my feet and then bounces back. And I just measure this time. Okay? And they get this value. So twice my height divided by c. Now, imagine that I do this as I am moved on a ray like this. And so my perception is that this ray of light travels straight from my head to my feet and back. For you, you see a different trajectory. It's like this one, because I am moving. Okay. Now, using the laws of mechanics, then you should modify the velocity of this wave and get the same time. So you would add up the wave velocity and the velocity with which I am translating with respect to you. Okay? But you cannot do this with light because for me, as well as for you, these waves always travel at the same speed. So since for sure it travels a longer distance for you than it does for me, then the time has to change. Yeah? So different distance, same velocity, equals to different time interval. As simple as that. Right? This very simple assumption is destroying the very belief of classical scientists like Newton, by whom the time is fixed and absolute. So this is really mind-blowing. Now, some other effect, which I will not detail, is the one important effect is the length contraction. So a body's length appears to contract when it is measured in a coordinate frame that is moving, which means that these two guys are moving with respect to one another, and so the green guy, so the green car looks shorter if observed by the red guy, and vice versa, of course. And then we have the upper speed limit. There is nothing, no information, no material object that can travel faster than light. This is an upper limit. So, let's go back to charges. Coulomb's law. So, charge is a fundamental property of matter, and you know that if you have two charges, then there is a force between them that can be either attraction or repulsion, depending on the sign. This force is always direct along the segment that connects the two charges. It depends on the total charge and on the inverse of the squared distance. You can simplify this and remove the effect of the second charge by using the concept of field. So this is the force that this charge would exert on a second charge, and this is a radial field, you see. So it is so the force lines are radial, so they go as rays from a center, and it depends on the squared distance. As simple as that. It is also important to note that I also want to let you know that this is linear with the total charge, and in particular this means that the electric field is radial, it changes with squared distances, and it is additive with respect to the sources. So if I have multiple sources, then the total field is the sum of the fields that you would have for any individual source. Based on these three properties, you can derive the Gauss's theorem, sorry, I'm always missing here, which say that the net electric flux through an hypothetical closed surface is equal to 1/epsilon 0 times the net electric charge inside the surface, which means that if I compute the flux, so the flux is the integral on the closed surface of the field multiplied by this ds, which is the phase set oriented normally to the surface, and this integral only depends on the total internal charges. If I have another charge outside this surface, this is not giving any variations. Okay. So we have, ingredient 1, Coulomb law, ingredient 2, Gauss's theorem. Ingredient 3, just consider a charge which is traveling with a constant velocity, very small velocity as compared to the speed of light, so it is very slowly moving. What is the field? Well, basically the field is just the field of these, you just get the field by translating the field according to the position of the charge. Now, and here finally my demonstration of radiation begins. Let's try to consider the field from an accelerating charge. So I am considering this case. I have a charge which is standing still, so it is an electrostatic field. At a certain point, someone kicks this charge away, and so at time t0 it is accelerating and it changes its position. And let's say that at a time capital T, it is moved by vt, where v is the speed at which this charge has been accelerated to. So we could say that the field is trivially moving with the charge. We could say that, but this would be against the principle that nothing can travel faster than light. And this includes the information that this charge has been moved. So this means that at time capital T, the whole space can be divided in two regions. Now, in the region where So in the region, let's say, outside of the sphere, whose radius is c by t, the information that the change has been moved hasn't arrived yet. Huh? Because nothing can change, can travel faster than light. So this means that in this region, in this outer region, then the field has to be exactly the same as it was before the change was moved. Otherwise, we would have a mean to say that something happened, but we cannot, because nothing can travel at that fast. Okay. Inside this region, the information has had the time to travel. And so inside this region, we do know that the change has been moved. So inside this region, the field is the field from this point. So let's say that the field inside this region is a radial field centered in this position. The field outside this region is a radial field centered in the original position of the charge. Is that clear? Accepted? Yeah. So if this was not true, then we could communicate, then instantaneous communications would be possible. Because I could be, so like I imagine that I have, you are sensitive to gravitational field, say, so you can feel the gravitational field of my hand, which depends again on the distance. So I just move my hand a bit, and you could feel in no time delay this variation, and we could use this very simple way to exchange communications independently on the distance in no time. Okay, but this is not possible. Why? Because now we can travel faster than light. Right? So if you accept that, then you have to accept that the space at this point, at time t, is divided into regions. So you have two different fields. Now Gauss comes in the way. Let's try to calculate the flux through this closed surface. It's EHGF. So I want to, I will choose this surface such that EH and FG are radial, and so there is no flux here. Okay, so the flux is only on this side and on this other side. Now, on this side, EF, the flux is given by the field outside this region. And so by the field that is originating from the original position of this charge. Inside this region, so where the information has propagated already, then you have to compute the flux by considering this other position. So since the charge is farther from this surface and there is no flux here, then it means that the net electric flux is not zero, because it is bigger here than here. Okay, the field is more intense outside than inside. But this is against Gauss's theorem, because it says that the net flux has to be proportional to the total charge inside this surface, which is 0. So, what is wrong? Well, Gauss is right, and the only solution to save, let's say, this reasoning and Gauss's theorem is to assume that when you move this charge, an extra field arises, and it has to give a flux in this direction. Okay, so when you move a charge, then a tangential field, meaning that it goes, it is not radial, it is orthogonal to this, pops up, and this is what you need to zero the flux through this surface. So, what is an electromagnetic wave? At this point, it should be clear. It is a perturbation of the static field caused by an accelerated charge. You have a charge, fixed field, static, it will last forever. You move this charge and you are perturbating this field. What you get is a tangential field that is propagating like this, so from the original position of this charge, and it is propagating with speed c, so with the speed of light. With more sophisticated arguments, you could also say that the intensity of this field is proportional to the distance from the source, and so no longer to the square distance, but just the distance. So another illuminating aspect of relativity concerns the interpretation of the magnetic field. And so I do this considering the Lorentz force. You know that if you have a wire that is carrying a current and a charge outside this wire which is moving with some velocity v, then you have a force between the wire and the charge, which depends on the charge and on the charge velocity and on the magnetic field. So to explain this force, you need to assume that this magnetic field exists, and this is what is is pushing the charge toward the wire. Now, let's analyze this solution. We have a current carrying wire. I will imagine the positive charges traveling here and negative charges are standing still. Of course, it is physically the opposite, but like in every other textbook, I will get this notation. And an external chain charge that is moving with speed v. So this wire is, so the net electric charge into this wire is 0, because you have as many positive charges as negative charges. So if you sum up, the total charge here is just 0. So you have to assume a magnetic field that is pushing the charge toward the wire. Now, in a relativistic interpretation, then we would just change the coordinate frame. So let's put ourselves in the coordinate frame of the external charge. So this is now standing still. the positive charges are standing still, again, because we are assuming that they move at the same velocity of our external charge, and the negative charges are moving with velocity minus v. So at this point, remember the length contraction. So a body's length appears to contract when it's measured in a coordinate frame that is moving longitudinally with respect to the body. So in the coordinate frame of this charge, these electrons are moving, so they appear to be contracted. This means that per unit length, so if you just cut a section of this wire, then there are more negative charges than positive charges. So this wire now has a net electric charge which is not zero. In this case it is negative, this charge is positive, and so there is a very simple electric field that is throwing this charge to the wire. As simple as that. There is no magnetic field here. There is just an electric field and length contraction. And by the way, again, with more sophisticated arguments, which I would not introduce because this is a course about weather imaging and not physics, but you can prove that you get the Lorentz, the law that describes Lorentz force. Okay, so this is it concerning radiation. So I didn't know this when I was a student, and I hope that you like this part. It is not for doing exercises. I mean, I didn't present you this for you to be able to solve exercises based on this, but I think that it is nice to understand radiation at a more intuitive level, and also to compare it to classical mechanical waves. Yet, when you want to do your homework, or when you want to design your system or to write your codes, whatever, I would strongly recommend to stick to Maxwell's equation, because I think it's much easier, or at least for us it is much easier, because we all started to study based on Maxwell equations. So just to present them, I guess you are both familiar with this. Okay, so I can go fast. You have the 4 equations. So the divergence of D is equal to the where is that? To the charge density. The curl of B is 0. The curl of the electrical field is equal to the time derivative of B, and the curl of the magnetic field is the current density plus the derivative of the electric flux. So you have this equation to relate these 4 fields, and these terms here, so epsilon, mu, and sigma, are let's say parameters to characterize materials at microscopic levels. Very shortly, permittivity is, let's say, is a measure of the resistance that is encountered when forming an electric field in a medium. Permeability is the measure of the ability of material to support the formation of a magnetic field, and conductivity is the ability of a material to conduct a current when an electric field is applied. Don't freak out. I put this just as a reminder. You have to, if you want to study electromagnetics seriously, then you have to know vector calculus seriously. This is just drawn from Wikipedia or something, just to remember the basic relations. If you have no problem with that, I can just skip it. Waves in free space, so you assume there is no free charges and no current. So the Maxwell's equation is simplified to these four equations. After some vector calculus, you end up with these equations. So you end up with a wave equation for each component of the vector field. And in particular, you know that if you have this equation, that this a solution of this equation is a traveling wave with velocity. So this term here represents the squared velocity, and so you can show that the velocity is the inverse of the square root of the product between mu and epsilon, and so you can also calculate the speed of light in this way. Plane waves. So I want to calculate the field, so I want to calculate a solution to this equation. Of course, I just consider a single component of the field for the moment. I assume that the field is only depends on two variables. So one is z, so just one spatial variable, and the other is time. And so what I get is that this is a possible solution where S is an arbitrary signal. So the field is S of t minus z divided by c. So it is just a delay. Of course, there should be a proportionality factor here to account for different numbers. This is not important. So, for example, in all the textbooks, I know plane waves are introduced in the frequency domain. So referring to a monochromatic wave, so a single frequency. I'd like to change this a bit and consider this signal S not as a sinusoid, but as a pulse, as a short pulse. So imagine that this S is a rectangular pulse, and this can be as well the signal that you are using to excite your antenna. And so the plane wave that you will be generating has this form. So this is S of t minus z divided by c in the case where S is a rectangular signal, and of course this is a snapshot at the fixed time t. So a plane wave is something of this kind. So the plane wave excited by a rectangular pulse is something of this kind. Of course, imagine that this is infinite, so this is a huge bag, but the thickness is just this one. And this thickness is the time duration of this rectangle multiplied by the speed of light. And this is a wave that is just so it means that the field has the shape of this bag, well, very large one, just like this. Okay, this is your plane wave. As simple as that. Now with some more vector manipulations, I also assume that you know this very well, so I'm really going fast. With some more vector manipulation, you can show that, well, this is for each component of the vector field. So you have a bag for the x component, a bag for the y component, a bag for the z component, but playing again with Maxwell's equation, then you end up demonstrating that there cannot be a vector component in the same the direction of wave propagation. So the field has to belong to this plane. And you can also show that H is orthogonal to E. And so let's say this is propagates this way. So this is the electrical field, this is the magnetic field, and they travel this way. There cannot be a field in the same direction of the propagation. And let's see how to write a wave. So if you want a formal mathematical expression of this concept, well, this is really easy. This is E, so this is an electric field, bold, because it is a vector, function of R, bold, so it is x, y, z, function of t, and this is a scalar. This is equal to E0, which is a constant vector, times this traveling term. And this is again the signal that is used to excite your antenna. And this is the exact variety of these situations here. Of course, this E0 does not have a Z component, so this E0 can be further written down as x plus, there is no Z. Let's now assume that the propagation does not happen in Z, but along an arbitrary direction. Then you can define P as a unit vector which is oriented in the direction of propagation. So P is a vector such that its modulus is 1. R is again x, y, z, and so you get this general representation of a plane wave. As again, think of the bag which is now moving in some of them in that direction. This is the most general writing of a plane wave. So in this case, with this process, so vector of t minus p times r divided by v, and this is the constant field, which of course we have to belong to this plane. And I think this is it. So I'm almost out of time. But we can consider again spherical waves. So, if you want to write a spherical waves, then you take another hypothesis. So basically, you look for a solution which is a function of the distance from a certain point and time. So you change the shape of the solution. You do a lot of calculations, and you are very happy because you see that this one can be a solution as well. But you have to consider also this term. So let S be whatever signal you like, then the field or any field component has this shape. So it is 1 on 1/r times the signal, which is now propagated as a function of the distance. So we are back to the case of a spherical wave described at the beginning, and we are also back to this dependency which was mentioned talking about when we were talking about the fields radiated from a moving charge. In this case, the wavefront is a surface of a sphere. If again we consider this kind of signal, so a short pulse, the wave at the fixed time t has this shape. So just, okay, this is not easy to draw. Just imagine, so like two spheres, one into another, and the field is only existing within these two spheres. And then they go larger and larger. Take care, because there is this factor, which means that the intensity is decreasing here, and I try to represent that by shading with this shading from where it's much clearer on my screen, from yellow to green. What about polarization? Well, assume that if you consider a conveniently small region of space, then you can always approximate the wave as a plane wave. And so all you know still applies. And so you have the electric field and the magnetic field. They have to be orthogonal, and they have to be orthogonal to the direction of propagation. Now, so what else? I like spherical waves a lot because they are the solution of Maxwell's equation in the case where a signal is transmitted by a point-like source. So basically, if you also consider the source term, which corresponds to the case where you have, for example, an antenna that is being excited by a signal S of t, I write the source in this term, so delta of R. This means that I have imagined that the source is just in a single point in space. So I am, how to say, neglecting, I am disregarding the physical dimension of my antenna. I am just pretending it is a single point. This is the equation that I get, and this is my solution. So I just get a spherical wave that is transporting the signal in the 3D space, starting from my source. Of course, if I change the position of my source, which means that I'm doing this, you see, this is again the same signal, but I am assuming that the point is not in 0 but in r prime. This is clear to everyone. Everyone is fine with this delta of space. Okay, good. And so you get the same wave, but from a different point. And of course, in the case where you have multiple point sources, then you can calculate the field simply by summing up all of the points. And so, in particular, this is important. This is the field. This is the total field that I get from these two antennas that are excited with these two signals. So I have this field from the first antenna. So S1 t minus the distance from the point R where I am considering this field and the position of the first antenna divided by C, and also remember the amplitude which is decreasing in the same way, and then the same for the second antenna. I just sum them up. Okay, and this is for today. I would like this to be the last thing I tell you. I would also like to know that this is very clear. So I'm finished, but I am open to taking questions. This writing is clear. Okay, excellent. So see you on Thursday.